Good afternoon. I'm Ivan Terribile. I'm a geotechnical engineer at CATI, and today I have the pleasure to present you two numerical studies regarding the pile penetration through the scour protection. So first, a bit of context regarding this geotechnical problem. So a scour protection consisting of a very coarse crushed rock layer is the most common solution to protect the offshore foundation from erosion which can affect the long-term performance of the foundation. This type of scour protection can be either pre-installed or post-installed with respect to the foundation. And to optimize the construction of the offshore wind farm, this is frequently pre-installed. So this means that in case of offshore pile foundation, the pile needs to penetrate the scour protection, and they are so exposed to the risk of initial damage at pile toe, which can further develop during the installation. And additionally, the scour protection can initially bear the pile self-weight, exposing the pile to the risk of pile run. So in this context, I will present you two numerical studies where the penetration of the monopiles were modeled with the discrete element method. So regarding case study 1, only the scour protection was modeled with the DEM, while the in-situ soil was modeled with a continuum approach. Then case study 2, both the scour protection and the in-situ soil were modeled with the DEM. So starting from case study 1, the aim was to model the monopile penetration through the scour protection and compare and validate the results with the monopile self-weight data that were measured during an installation campaign. So in this context, we selected a specific location, and the S-build data of the scour protection we used to to build the model, the numerical model. In particular, the scour protection was composed by two layers, so an armor layer over a filter layer, both with an average thickness of 75 centimeters. The armor layer was modeled in PFC 3D with the polyhedral blocks, while the granulometric curve of the filter layer was modeled in PFC 3D with spherical elements. So an important part of the DM modeling is the calibration of the soil behavior. In this case, triaxial test, simulation of triaxial tests were performed on PFC 3D in order to calibrate the microscale parameters of the contact model and in order to achieve the target angle of internal friction of the material. So once the contact model was calibrated, the model was built. To reduce the computational time, taking advantage of symmetry, only 1/4 of the entire size was modeled. The seabed was modeled as an elastic continuum in flak, while on top of it, the filter layer and the armor layer were modeled with discrete elements with their actual volume. Finally, the pile was generated as a rigid element. The numerical analysis was divided into two phases. The first phase simulated the monopile self-weight. Being during this phase, the monopile restrained by the crane, a displacement control analysis was performed. So a prescribed displacement was imposed to the pile until the soil reaction to the monopile penetration reached the monopile self-weight. The second phase simulates the hammer positioning. During this phase, the monopile is not restrained by the crane. It is free to accelerate under the hammer load. So a load controlled analysis was performed. Both the load increase rate and the displacement rate imposed were derived from the crane data. So in terms of results, a good match with the experimental data was observed for the selected location in terms of penetration under self-weight. These results was obtained considering an angle of internal friction of 45 degrees for both layers. Then a plateau is observed when the monopile toe reached the filter layer, and some oscillation of the resistance can be observed and can explain the different self-weight penetration observed over the wind farm for a monopile with similar weight and a similar configuration of the scour protection. Finally, the increase we can observe when the monopile toe reach the seabed is a boundary effect due to the fact that the seabed was modeled as a continuum, an elastic continuum. So the experience gained with this first study was then used to improve the modeling on a second project on a similar subject. In this case, the aim of the study was to model the monopile penetration through the scar protection layer and through the in-situ sand. In particular, the in-situ soil was characterized by 2 layers of sand, so a dense sand over loose sand, and the scar protection was composed only by the filter layer with a thickness of 75 centimeters. Same approach was followed to model the parameters, the soil behavior, so running triaxial test simulation in PFC 3D. Regarding the numerical model, in this case, to reduce the computational time, a trench model was built. And the model was reduced to 1/16 of the entire size. The discrete elements were modeled only within the trench, so in proximity of the monopile, while the rest of the volume was modeled as an elastoplastic continuum in FLAC 3D. 2 different profiles were studied. So with profile 1, where the thickness of the dense sand layer was limited to 2 meters, and profile 2 with a thickness of the dense sand layer of 4 meters. So in terms of numerical results, in both cases, the monopile has penetrated the scar protection, stopping in the dense sand layer. For profile 1, which is characterized by a limited thickness of 2 meters of the dense sand layer, a pile run is observed in the second phase of the analysis when the hammer load is applied, with the pile rapidly accelerating through the loose sand. In all cases, a sudden reduction of the end bearing is observed when the monopile tip approaches the top of the loose sand. And good correspondence with the unit with the end bearing factor and unit skin friction was observed comparing the results with the literature value. Finally, it's possible to observe also an increase, a local increase close to the pile tip in terms of shaft friction. So, in summary, I've presented 2 numerical studies that were performed with the aim of better understanding the interaction between the monopile and the scour protection layer, a pre-installed scour protection layer. The case study 1 indicates the capability of the DM modeling of reproducing with good accuracy the monopile self-weight penetration, as indicated by the comparison with the experimental data. For case study 2, the aim was to model a complete penetration of the monopile through the scar protection and through the in-situ sand. This allowed to model a punching phenomenon and the resulting pile run. And finally, a benchmark of the model was obtained comparing the end bearing factor and the unit shaft friction with the literature value. So, in conclusion, the obtained results confirm the robustness of the applied methodology and encourage the application to more challenging cases. Thank you.